Thanks to our understanding of plate tectonics, we know the basics of how continents move and form. But figuring out how specific features formed is harder than it might seem. And some of the features can be pretty big, like this big. Even today, scientists don't have all the details about how mountain ranges like the Alps and the Himalayas formed. But there is hope in the form of garnets. Researchers are turning to these pretty little stones to do the heavy lifting in understanding some of the largest geological structures on Earth. People have been using garnets in jewelry since the time of the Egyptian pharaohs. They're typically dark red, but garnets can come in a range of colors from yellow to orange and even green. That's because their chemical composition can vary a lot, while still technically being classified as a garnet. They're kind of like a whole bunch of crystals in a trench coat. Generally, they're silicate minerals with a cubic crystal structure and a variety of metal ions comprising the rest. Most commonly, you get aluminum, calcium, manganese, magnesium, and iron. But there's a range of other elements and novel combinations that can all add up to one garnet. And scientists think there may be even more that they haven't even discovered yet. And while we still may not have uncovered all the secrets of garnets themselves, we've been using them to help us understand complex geological processes for over 100 years. It all started back in 1912, when a British geologist named George Barrow was mapping metamorphic rocks in the Scottish Highlands. He and his team noticed clear delineations in the rocks where specific minerals appeared, and he used them to define metamorphic zones of increasing temperature and pressure, which we now call Barrow zones. These zones are, in order, the chlorite, biotite, garnet, staurolite, kyanite, and sillimanite zones. And while they were first observed in Scotland, they can be found all over the world. And these are what's known as index minerals. That is, they're part of a spectrum of minerals that act as indicators for the conditions that a metamorphic rock's been through. We know that garnets only form when mudstones experience high enough temperatures and pressures, kind of like how bread dough will only start to rise if your kitchen is warm enough. But if geological conditions exceed the values that make garnet crystals, the elements in the rock will assemble into a different kind of crystal instead. So by simply logging the minerals that you find in a rock, you can work out the peak temperature and pressure that that rock experienced. And this isn't just neat trivia. We can use it to help us understand really complicated geological processes, like how mountain ranges grow. See, when tectonic plates collide, rock layers get shoved deep under the surface. And the deeper they go, the hotter they get, and the more they're squeezed, and the further along Barrow's zones they progress. So just finding garnets in a metamorphic rock tells us that it has experienced temperatures and pressures at the middle of the Barrow scale, which tells us a lot about how much force it took to make those mountains. And while that's true of all the index minerals, garnet is special for another reason. As garnets form, they tend to incorporate certain elements into their structure at different temperatures and pressures. Kind of like how you might crave a hot cocoa when it's freezing out, but not in the middle of July. But instead of cocoa, garnets grab up manganese when the temperatures swing lower and switch over to magnesium when the temps get higher. Researchers can use that as a sort of mini index within the full index scale. By looking closely at paper-thin sections of garnet-bearing rocks to see what elements they grabbed as they grew, scientists can reconstruct the precise journey of that metamorphic rock through the Earth. Plus, garnets can continue growing as a rock moves and the surrounding conditions change. So they end up with growth zones starting from their cores and extending outwards that contain a detailed record of the ordeal they've been through, just like rings on a tree. And not only that, but garnets growing in a metamorphic rock can also trap tiny slivers of other minerals present in the rock, protecting them from later alteration and literally giving us a window into past conditions. In the Italian Alps, researchers were able to use garnets to map the conditions under which the continental crust was buried. Scientists found that garnets from the southern part of the mountain range contain a mineral called coesite, which only forms at very high pressures. Coesite normally breaks down before it reaches the Earth's surface, but it was protected inside the garnet. So the coesite is proof that the rocks were heated to more than 700 degrees Celsius and squeezed to around 35,000 times atmospheric pressure, all at an incredible depth of 120 kilometers. Meanwhile, garnets from the northern part of the range show chemical zoning that suggests they formed under much lower maximum temperatures and pressures. Based on this evidence, scientists conclude that this part of the Alps is actually made up of slices of metamorphic rock that formed under different conditions, which have since been squished together into one mountain range. And this isn't the only place that zoned garnet crystals are shedding light on mountain building. And garnets may even help researchers settle an ongoing debate over exactly how the Himalayas are forming right now. See, there are two competing models for just what's going on between the Asian and Indian plates to build the Himalayas. One theory says that the central Himalayan range is formed by a channel of hotter material that's pushing up between cooler rocks, sort of like melted cheese squeezing out of the end of a grilled cheese sandwich. But another option is that the range is built from slices of cooler rock that are progressively thrust up on top of one another, a bit like building a layer cake. If model 1 is right, then the garnets would record an increase in temperature without much change in pressure, whereas stacking of rock slices would cause an increase in pressure without much change in temperature. And analysis of actual garnets from specific spots in the Himalayas show that they've experienced high pressures, but not particularly high temperatures, which fits with the stacked slices model. And as an added bonus, researchers have been able to use the garnet inclusions to run radiometric dating and figure out just how old the Himalayas really are. It turns out the Himalayas are at least 10 million years older than researchers had previously thought, and likely began to form in the Eocene epoch. So geologists continue to use garnets to solve some major tectonic mysteries, which is pretty neat for a gem that's usually small enough to end up on a ring. And in fact, we think garnets are so neat that we decided to share them with you all in this month's SciShow Rocks Box. Subscribers to the Rocks Box will get a different mineral or fossil every month delivered right to you. And it comes in this fancy little box. You can find out more by clicking the link in the description down below. And if you are interested, do not act on a geologic timescale because these things always sell out fast. But either way, thank you for watching and learning with us here at SciShow.